wait for the. Okay, and our next talk is from Mert Karakaya. I hope I pronounced that somehow correct. And I'm really looking forward to that because it is about behavioral teleporting, and I'm very curious about to learn about what is meant by this term and how this works. So please share your screen.
Yeah. Thank you for having me, first of all.
Yeah.
I'm very excited to share our work that we have recently, we have completed last year, the first part, and we are on the completion of the second part of the work. Yeah, sorry if my voice cracks or I might do some mistakes. It's early in the morning here in New York. So I apologize in advance.
But you can be in New York, so that's the upside.
Yeah. I mean, I don't know if you want to be in New York during COVID times like we have been here.
True.
But yeah. Yeah, so I'm Mert Karakaya. I'm a PhD student at the Dynamical Systems Lab at NYU Tandon School of Engineering. My advisor is Professor Porfiri, and this work was in conjunction with our collaborator Simone Macrì from Istituto Superiore di Sanità. And today I will present our work on behavioral teleporting and especially our new results on the acute citalopram administration with the behavioral teleporting. So thank you again for having me at the conference. I'm very excited, and I hope I can give you a pleasant experience through this presentation. So during the COVID times, we all wanted to be somewhere else. And as an international student living in the US for the past 8 years, this is especially true for me that I wanted to be close to my family. I wanted to be out of the quarantine. But how can we do this? Just like in Star Trek, we all wish that we could teleport to some place easier instead of taking the planes for many hours or taking any other commute, that we could just snap our hand and be somewhere else. But we all know that it's not possible yet through our current technological implementations. So what if we use the robots as our extension of ourselves to interact in real life? And this only does not extend to the travel. Sorry, I don't know why it keeps skipping. But it can also be used in different aspects, like such as when we build colonies in Mars and you don't have a specific doctor in Mars, can you use a robot to interact with the patient? So to study the first part of this, we did not look at the social behavior in humans, but we looked at the social behavior in other animals. Since social behavior is defined as the interaction between two or more organisms within the same species, and it's common to most animals, we thought this could translate across the animal kingdom. And especially we looked at the problems between this teleporting of how the individual characteristics, morphological differences, and environmental situations alter their social interactions. Our model of choice was zebrafish, and I'm sure some other presenters might have presented with zebrafish, since it's a highly accepted model animal in the scientific community with over 10,000 papers published every year. Due to its social behavior, homologous genetics, and other aspects matching humans closely, along with the regenerative abilities that it has for the medicinal part. One important aspect is zebrafish can be used for pharmacological studies, since it has similar response to anxiety-related drugs such as serotonin, selective serotonin reuptake inhibitors and such. So we know that, as also Donato explained in his presentation, perception in fish relies heavily on the visual cues. And it was demonstrated that many things can influence the interaction between the fish, such as the aspect ratio, tail beat frequency, the noise of the robot, the color, and the body size of the fish. So in our work, we try to consider, well, the body size of the fish, most importantly. But this was the debut work of our behavioral teleporting to show the scientific community, which was published in iScience last year. So how our behavioral teleporting setup works is we basically have two robotic platforms with two experimental tanks, right? I'm not sure if you can see my cursor. Can you see my cursor? This would be better. Okay.
I cannot see it.
Okay, now is
Now,
it
now I
better?
see it. Now I see
Okay,
it. Sorry.
great.
Yeah.
So
It's
we
pretty
have,
small.
okay. So we have two robotic platforms, sorry, under two tanks, and each tank has a conspecific replica of a fish and a real fish. And then we track both the conspecific replica and the fish using two webcams connected to a computer and track their position in real time, which was, I would feel like, was the hardest thing to do, to reliably track in real time. And then what we do is feed the position and speed, as well as the direction of the fish on the left to the replica on the right, and the fish on the right to the replica on the left. Using this setup, we wanted to study the validity of it. So what we have done is to look at the effects of body size between the fish. So for this, we have created 4 different replicas based on the measurements of our fish. So we measured 12 pairs of fish and separated them in terms of small and large sizes, making sure that there's an average of 1 centimeter of length difference between the two fish. And based on our average measurements, we created female and male replicas of large and small sizes. So as you can see, this is our behavioral teleporting in action. And this tracking has not been done again or has been smoothed. This is actually the experiment taking in place. So there could be some errors, but we tried to follow the fish as closely as possible with our replicas to allow the two fish in different tanks to interact as if they're in the one same tank through the use of our robots. So we asked some questions. Will the pairwise interactions between live animals be preserved with proxies compared to two fish swimming in the same tank? Or how will the body size change with the pairwise interactions? So to study these questions, we came up with 3 conditions. The first condition was the control condition, where we had 2 fish of different sizes, small and large. And then we came up with 2 behavioral teleporting conditions. The first one was the match condition, where the size of the replica matched the fish it was mimicking. And we also came up with a mismatch condition when the size of the replica did not match the size of the fish it was mimicking. So in the match condition, we expect a similar response to the control, since it would feel like as if a small and a large fish is swimming together. However, in the mismatch condition, the fish of equal size will be it will be seem like they will be swimming together, since the replica and the fish will be of same size. However, the behavior of the replica would be of opposite sized fish. So to quantify the interactions, we used information theory. I'm sure if you have listened to the talks of Professor Porfiri on fish, you must have heard about transfer entropy and information theory, since we really like to do these analysis, and it can really reveal the interactions between complex systems. So you might ask, what is information theory? So we use Shannon entropy to understand the complex dynamical systems. So Shannon entropy is a probabilistic approach can, and we can simply explain this from a toss of a coin, right? Imagine we have a fair coin. So the outcome of the coin would be either heads or tails, right? So when we have a heads or tails, if you plug it into this mathematical expression, what we find out is the maximum entropy is reached because the most amount of information is encoded in the uncertainty of the outcome because it has the 50-50 chance. So we have one entropy. But again, imagine the coin that either have both heads or both tails on both sides. Now we have no uncertainty in the predictability of the outcome because we know it will be heads if the both sides are heads, or it will be tails if the both sides are tails, which is given by the 0 and 1 probability values. So our entropy would be minimized and is 0. So what transfer entropy looks at is the reduction in the uncertainty of the predictability of the outcome. I know it's like a kind of like a word play, it might sound like, but to explain it in simpler terms, right, I would like to use this diagram. So imagine there are gazelles that are just having their food, and then the cheetah approaches in the background, right? And then gazelles realize that there's a cheetah and they start chasing each other away. As the gazelle turns right, cheetah also turns right. And gazelle turns left, cheetah also turns left until the interaction is finished. So what this means is by looking at the past values of gazelle and the past values of cheetah's behavior, for example, can we predict the current state of the cheetah? So for example, can we predict that when the cheetah gazelle turns left, would cheetah turn left? And this would in fact be true because the uncertainty in the predictability of the outcome of cheetah would be reduced since it's interacting with the gazelle. So by applying this method to our experimental results, what we have found out that there was an information transfer between the small and large fish and large and small fish in both directions in the control condition as expected, two fish swimming. But this was also true for the match and mismatch condition, which means that through our behavioral teleporting platform, the social interactions are preserved. And specifically, we have also looked at the net transfer entropy to see if there's a leader in the relationship. And in control, what we have found out that the small fish led the large fish in the interactions, even if it could not be a leader, but it had basically a positive interaction from the small to large fish. And this was also true in the match condition. However, when the sizes did not match in the mismatch condition, there were no net interactions observed between the fish. Yeah, so this simple diagram explains it, whereas the dashed lines show the transfer entropy between the two fish, and the bold black line shows the net transfer entropy. And the conclusions that we can come to it is small fish leads the interactions. And I think one certain thing to say is it does not mean it's the leader, it just leads the interactions. Same as the cheetah and the gazelle. Maybe the cheetah is the driving factor, but then the gazelle can lead the interactions because it will do the motions before. And behavioral teleporting preserves the interactions, and also the morphology plays a critical role. Again, getting inspired by the quarantine, since it's been a big part of our lives, we saw that there was a record increase in the prescriptions for anxiety-related medication, especially SSRIs. And then it was found that social isolation is one of the main factors contributing to anxiety. In fact, 78% of all antidepressants, anti-anxiety, and anti-insomnia prescriptions filled in the week of March 15, 2020 for new patients. And you could see the increase in the drug usage of anxiety-related medicine in the UK in this chart. So we said, can we use our behavioral teleporting platform to see how the social interactions altered when we use these anxiety reducing medicine? So for that, we have come up with a series of conditions to use with our behavioral teleporting platform. And then we have chosen 3 concentrations of citalopram, which is a selective serotonin reuptake inhibitor. So we have looked at 0 milligram concentration, 30 milligram concentration, 100 milligram concentration. And we took all combinations of these 3. So we have 3 similar concentrations, which I will refer to as same conditions. So 0, 0, 30, 30, and 100, 100. And we have different conditions, which I will refer to as 0, 30, 0, 100, and 30, 100. So in our procedure, we tested each condition for 12 trials, and we randomized the order of conditions each day, as well as the side of the fish that we put in. And for each trial, fish were subjected to acute citalopram administration in a beaker for 5 minutes. That was controlled with temperature at 26 Celsius degrees. Then fish were allowed to habituate in the experimental tank in an opaque cylinder for 5 minutes. Then we run the behavioral teleporting for 15 minutes. To quantify the interactions between the 2 fish, we investigated 2 metrics of shoaling and schooling. In fact, it will be 3, but I'm still investigating in 5-minute segments. And so far, what we have looked at is the inter-individual distance and polarization. Also, we have investigated the information transfer between the 2 animals. So our preliminary results, these are not final, we're still analyzing our results, show that for the shoaling and schooling parameters within the same conditions, so that's again 0, 0, 30, 30, and 100, 100, we do not observe any significant difference for polarization or distance across conditions. And this can indicate that when both fish have the same level of anxiety, so when they're treated with the same amount of citalopram, their social interactions are maintained. However, when we look at the shoaling and schooling across different, for the fish that were treated with different concentrations of citalopram, even though we do not observe any significant difference for polarization and distance, we observe a trend across the condition, where for polarization, the anxiety levels of the fish are reduced as the citalopram concentration of both fish increase. And there's a differential response in the inter-individual distance as the difference of concentration increases. So when there's 30, it's minimum. When there's 70 milligrams of difference, so a low concentration and a high concentration of citalopram, it's increased, and it's maximum when there's no citalopram and maximum citalopram. And this can somehow indicate that the social interactions are reduced as the anxiety level of fish are reduced unequally. So one explanation that we have in mind is less anxious fish might be less inclined to interact with the more anxious one. So for example, if a fish is treated with 100 milligrams of citalopram, it might not want to interact with the 0 citalopram one, since it's more relaxed and it might be more anxiety inducing to interact with the other fish. So of course, like our previous work, we have looked at the information transfer. And in the opposite case of the shoaling and schooling results, we observed a significant, almost significant results for the same condition, where there was a difference between 30 milligrams of citalopram, like 30-30, and 100-100 milligrams of citalopram. And this actually matches our previous results when we have done experiments with citalopram, because we have observed the highest response to citalopram administration at 30 milligrams of per liter, whereas at 100 they almost became sedated and their social interactions were reduced with both the conspecifics and also the replicas. So this we can observe through information transfer as well, whereas we did not observe any significant difference in the different condition. Yeah, so these are our results so far for this work. So we are still in the works for analyzing our results and adding more methods, and we hope to finalize this work and publish soon, which we hope that we can get something nice and then show that the behavioral teleporting can be used more than just the first experiment that we did. So thank you for listening to my talk. I guess I was talking a little faster, so I've been a little earlier up time, but I would like to thank the National Science Foundation and National Institute of Health for sponsoring our research and creating the funds, as well as I would like to thank again my advisor, Professor Porfiri, and our collaborator, Simone Macrì, for guiding me throughout this work and helping me. Yeah, thank you.
Thank you for this very nice presentation. I think we have about like 5 minutes for questions. Feel free to raise your hand to ask a question or type it into the chat. Okay, so in the meanwhile, I would like to ask a question. You could potentially make these chains or these connections between the fish, which is sort of mediated through these robots. You can also form like a ring, a larger one, right? So like, is this possible?
So I don't
That
understand what you mean by
like you have like 4 fish, for example, and then like the information is always carried over pairwise. So they only see a second fish, but it's not mirrored back to them, but through a loop through other fish. Is something like that, different topologies possible, or is it just working pairwise?
We could also do it. Yes, you're right.
Yeah.
We could set up the experiment that way. But unfortunately, our current limitation is the response time of the robots, right? So previously, when we had a single robot, so I'm sure Giovanni presented in the earlier sessions, the work with the predator and the robot, right? I don't know if you guys have listened to it. And in that experiment, we also done a closed loop where we were tracking the fish and the robot in real time. And we were only able to do at 20 hertz, so 20 frames per second rate. In this case, what we have done is we tracked the fish in 20 frames per second, but we were only able to control the robot at 10 hertz because we use Arduinos to control the motors to transfer the digital signal to analog. And unfortunately, some bottlenecks are created in the Arduinos that reduce their response time. So the more robots mean less response time. So the behavioral teleporting might be disconnected. Of course, it is possible to do for the ring, as you have mentioned, and it's a great idea, actually. So I will definitely talk with Professor Porfiri to see
I'm
what
not
we
sure.
can,
I'm not sure
what
that
we
this
can do.
can work out because then it will not reflect it back to the first fish, but like to another one, and then. So I was just curious if there are other topologies possible with such pairs or not. I'm not sure that it is really making sense. So
yeah, I'm sure it's possible, but I think from the technology aspect, from the engineering aspect, we have to improve the robots much more. because as I mentioned, it's like 10 hertz right now, so it's like 100 milliseconds
Mhm.
of a response time, so it causes about 200 milliseconds of delay
Mhm.
in the mimicking of the behavior when it goes back and forth. And what we have observed is the 200 milliseconds is the maximum a fish will allow for it to be realistic. So when you do the four times, when it comes back to the fish, when it starts, it will be maybe half a second or more when it comes back to it as a response.
Mhm.
So there might be some disconnections. Does it make sense?
Mhm. Yeah.
Yeah,
Yeah.
but it's definitely a good idea. Yeah.
I'm not sure that it is a useful idea. Let's say it. I was just wondering. Uh,
Yeah.
Another question that I always have in mind when I see these fish experiments with robots, and I could have asked it also to previous ones, but there was so many other questions, so I didn't get to ask them. So, like, I want to ask you. Um, we when we do these experiments, at least it looks to me, all these aquariums, these arenas seem to be very unnatural, and so they are like plain empty. I remember, for example, the Donato has shown the neonfish, and pretty sure they live in a very, very highly structured and dark, shadowy environment. But usually in these experiments, because of the high-speed tracking that is often needed and so on, it is like bright light. It's even like brighter than on a stage or something sometimes. Uh, how much does that affect the natural behavior of that fish? So how much does it stress them to be uh, in the spotlight that much, for example, with
Actually, that's
no hiding place around and so on?
yes,
Yeah,
that's a great question. And when we do these types of experiments, we want to find the arena that they can hide the less.
yeah, yeah, of course, yeah,
So that is a great question, actually.
yeah.
So as you can see, our experimental tanks were chosen as green, which was shown to be one of the most natural looking environments in the
Mm,
previous works, if I'm not mistaken, by Dr. Rodrigo. Yeah, from the top of my head. But like, yeah, she has done a paper where they looked at the different backgrounds of white, gray, green, blue, and what they have done is green is the most soothing to fish, especially zebrafish, and it's the most natural looking one. So we wanted to choose a green environment, and we wanted to keep our lights under 200 lumens. Sorry, 200 lux for the environment, and in this case, it was about 70 to 90 lux.
mm,
Uh, to reduce the anxiety in the fish, also create a more natural looking environment.
mm,
Of
mm,
course, there are no any hiding spots or like any rocks or anything, not even any corners that the fish can hide.
mm.
So
But
that's
that
a
level
great
is rather,
question.
level is rather dim. So um, I was wondering, is the camera then still? I mean, obviously it is, but it surprises me because whenever we did tracking of
Uh-huh.
bees where I come from, the people who do the image tracking are always asking us like put more light and more light and more light. Uh, so you don't run into that problem,
No,
obviously.
I don't run into that problem. And of course, like more light is always better and more preferred.
Yeah.
But as I explained, like I did the most work in tracking for this. Like previously, I worked like 4 months on tracking, doing like different pilots and trials to get it just right that it would work, but
Mm,
also not be intrusive to the fish behavior and cause more anxiety.
mm, mm.
So that was the hardest part of it. Of course, I could have increased the light and had more
Yeah.
stuff, but I wanted to keep it as dim as possible.
Mm,
And in your other questions, like, can we do with the obstructions and like other environments, right? Can we add plants? Can we add rocks to the environment? That actually like makes me really happy because another collaborator working with our group to actually make that possible. So Dr. Boutel from Northern Illinois University is working with us on developing a tracking system that is able to identify the behavior of zebrafish, because our focus is on zebrafish, in enriched environments where we have plants, we have rocks, and we have other obstructions of fish. And then hopefully we'll get to share that work soon with the scientific community, which will be useful to everybody, I feel like, for the tracking.
Yeah. So you always have the problem that on the one hand, you want to exclude all other factors in such an experiment, but you also want to observe natural behavior, and then like you are in a sort of conflict, I guess,
Yes,
too.
yes,
Like
yes,
we are, for example, when we
yes,
have to observe the bees under red light, and then the cameras are underexposing and so on, and yeah, gets
yeah.
difficult. So we have to move on. Thank you very much.
Thank you.
And